Hello everyone, my name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering in department. Okay, today I would like to explain about the chip formation and breaking of the chips. What is the need to break the chips? This one is the course outcome of this topic. Recall the importance of geometry of cutting tools, coolants, and tool materials for analysis of material behavior during manufacturing processes. Okay, so we'll see first of all types of chips. There are three types of the chips. Um, so first one is the continuous chips. Second one is the discontinuous chips. Last one is the continuous chips with build-up edges. Why this build-up edges will form in machining? We'll see what is the reason behind that. Also, we'll explain about that one. So we know that this is the just machining process. This one is the workpiece. You know this one. The tool moves in front of against the workpiece. During that process, the material, the portion which is in front of the tool bit, this material will be deformed. So when the force is increased, force of the tool increased the yield strength of material, automatically the material will be removed or will be sheared from the workpiece. So you know this one, this process. Here, so in this process, due to the friction, some heat will be developed in some regions. Mainly, this one is the primary region. This is the in front of tool. So this is the primary shear region also. So next one, this is the clearance angle. You know this one. Here also the friction, due to the friction between the workpiece and the tool, here also heat will be generated. So next one, here also the interaction between the chip and the tool, here also heat will be generated. Okay, so maximum amount of heat will be dissipated by the chip. So this is the chip, you know this one. So you can say this is the secondary shear zone. First is this one is the first shear zone. So material will be removed from this shear zone. You know this one. This chip will slide on the surface of tool. That is the you know that rack face of the tool. You know, we already discussed in previous classes. This is the general machining process, single point cutting tool machining process. You know this one. Here you can observe this diagram. This is the continuous chip formation. The chips forms in the form of curls like this one. So here this one is the discontinuous chip formation. Here the chip formed in the form of segments. So this is mainly for the brittle materials like cast iron, like this one. So this is the continuous process like mild steel, all this one. So here for the ductile materials, here you can see build-up edges due to the overheating, the heat. So overheating between the chip and the tool. So this chip will be welded with the top surface of the or rack surface of the tool. So this is the welding portion. So this is nothing but to build up edges. So due to this one, the chip will not move or slide on the surface of the tool bit automatically. That leads to rough manufacturing or rough finishing of the surface also. We will see one by one what is continuous chip formation and what is discontinuous chip formation, what is the reason behind that one, what type of materials will give the continuous chip formation, so what type of materials will give the discontinuous chip formation. So we'll see all these things. So before going to that, these are the conditions for continuous chip formation, how to consider this one. So the sharp cutting edges, low feed rate, and a large rake angle. So it is very important. So for the ductile materials, we will see the continuous chip formation. So high cutting speed here we will see. So V is equal to, and then low friction will form uh, at the chip tool interface also. So these are the conditions for continuous chip formation. The first of all, we'll see the uh, continuous, discontinuous chips here. So this is the, so due to this tool bit, the material will be removed in the form of chips like segmental chips like this one. This is also called as the segmental chips. So these are mostly occurred while cutting brittle materials like cast iron, okay, or low ductile materials also. So instead of shearing the metal as it happens in the previous process like continuous process, here the metal is being fractured like segments of the fragments and they pass over the tool faces. So like this segments metal easily breaks and the in the form of in the form of segments, the material will be removed like segment type chips. Okay, here the advantage of this one is the tool life is more here, and the power consumption as in the previous case so is also very low. But in continuous chip formation, the chips formed in the form in curling process or curling shapes. So mostly this type of continuous chips occurs in ductile materials like mild steel, those things. Okay. So here we'll see the continuous chip formation like this one. So continuous chips will occur in this continuous process. Okay, for this one, these are the main conditions for producing the continuous chip formation. So this is the discontinuous chips you can see. Yes. So we'll see discontinuous or segmental chips. So it consists of separate plastically deformed segments. You know this one. Produced during machining of brittle materials like cast iron or bronze also. Okay. The main advantage of segmental chips or discontinuous chips is uh, easy to handle. You can handle the manufacturing process or finishing process easily, and low power consumption also it will take, and reasonable tool life. So we'll get good tool life. So by this discontinuous process, segmental processing, chip formation. Next, fade surface finishing also. Here we'll get the good surface finishing. So it is produced in machining mainly uh, ductile materials under the following conditions. So high depth of cut here we'll see, and low speed also here will give. So next, a small rake angle is enough for this one. So not desirable for the ductile materials, because so for the ductile materials in for continuous process we require the high rake angle and a high speed and a low depth of cuts, the opposite to this one. Okay, so next one, continuous chips. The main advantage of the continuous chips, you know this one. So here metal continuously deforms without any fracture and flow over the rack face of the single point cutting tool. So in the form of just like curling process like ribbons. Okay, so produced in machining ductile metals, mainly this type of chips formed while um, machining processes, ductile machining processes. So under the normal cutting speed. Okay, so it produces the small depth of cuts and normal to high cutting speeds. So normal to high cutting, so it requires a high cutting speed and slow, less depth of cut, and it requires the large rake angle also. If, if you provide the large rake angle, so the finishing of that surface finishing will get good surface finishing also. Okay, reduce to friction along the chip tool interface. Okay. So next, most desirable chips indicates stable cutting results in generally good surface finishing. Here we'll get the good surface finishing. So the main disadvantage of continuous chips. So continuous chip formation is the good processing for for getting good surface finishing. We know this one. The main disadvantage of this one is the difficult to handle and dispose of. So because continuous kernel type ribbons or kernel type chips are formed, so that disturbs the machining process of operator or surface finishing also. They disturb the surface finishing also. Next, chip coils in helix form, so around the work and tool, and many cause injury to the operator when it breaks loss. Okay, so that is the main disadvantages. Next, chip breakers are necessary here. So breaking of the chips are very important here. So continuous chip that shows the that gives the good surface finishing, but you have to cut the chips, continuity of the chips. Okay. So more frictional heat here generated due to longer duration of chip contact with the rake face. Okay. So due to that, so longer duration of chip contact, so automatically due to conduction, heat transfer takes place morely here. Okay. That is the main disadvantage of the chip formation, continuous chips. Now we'll see discontinuous chips. Already we so this is the discontinuous chips with the build-up edges. We'll see this one. Why this type of edges will be formed while machining. Okay. So when cutting a ductile material, so the compression of the metal is followed by high heat at tool face. You know this one. So due to the high heat between the tool and the workpiece, the chip. So there may be chances to welding. So formation of weld between the chip and the rake face of the tool. Okay. So this is in turn enables the part of the remove the metal, so to be welded in the into the tool. So because of this one, we'll get the this produces the rough surface finishing. The tool life may be also reducing. So because of this chip formation, so the interaction, the heat between the chip and the tool surfaces, some welding will occur between the chip and the tool. So that opposes the free sliding of the chip on the tool bit. So automatically that leads to rough surface finishing also. So that is the main disadvantage of the build-up edges. You have to rectify those things also. Okay, is this type of build-up edges. It means welding of so welding between the chip and the tool face, rake face will generate. Okay, so due to high heating. So build-up edges are characterized by its shape and size and bond strength also. Mainly it depend upon the workpiece material, stress and temperature, like cutting velocity and feed. Okay. So next, cutting fluid application governing, cooling and lubrication. So for rectifying these build-up edges, you have to provide the lubrication fluids. Okay. Uh, for this one. Next, we'll see what are the characteristics and effects of build-up edges also. Effect of build-up edges formation. So unfavorable rack angle. So because of this one. Next, we'll get bad surface finishing due to this build-up edges, because the chip doesn't slide freely on the rack surface. Okay, next to tool life will be reduced. Okay, tool life will be reduced here also. Next, the fluctuations of cutting forces also occurs due to this build-up edges. Okay, these are the main effects of build-up edge formation. So how to avoid this one? There are some methods to avoiding this build-up edges formation. First one is the increasing the cutting speed by increasing the cutting speed. Next, decreasing the feed rate, feed. So less cutting amount, cutting depth of the material. Next, to increasing the rack face also, rack angle, and improving the cutting fluid system. So by effective supplying of the lubricating system, then you can rectify this one. You can avoid this build-up edges. Okay. So these are the just like types of build-up edges you can see. This one is the positive edge uh, build-up edges. This one is the negative type of build-up edges you can see. Here the flat type of build-up edges. There are three types of the build-up edges. You can identify the build-up edges by their shape and the strength, and so strength. You can observe this one. So finally, this one is the discontinuous chip. So chips formed in the segmental form. This one is the continuous chips. So chips will be removed from the material in continuous chips like viral type. Okay. So like ribbons. So continuous chip with build-up edges here also. Some build-up edges will be found between the chip and tool face. You know this one. So this one is the some inhomogeneous chip formation, not homogeneity. Some so we'll see chip formation in irregular forming of chips also. We'll see this type of. So based upon the chips, we can understand the just processing also. So based on the chips, you can understand the which type of material also. Okay. so study of chips are very important in machining processes. Okay. So you'll see what is the defects of, what is the drawback of the continuous chip formation also. We'll see chips will develop a curvature like this one, chip curvature. So as they leave the workpiece surfaces. So we'll see the factors which are affecting the chip curl conditions. Okay, they this continuous chips, curling chips disturb the stresses, distribution of sorry distribution of stresses in primary and secondary shear zones. You know this one. So this is the zones. This is the chip formation. Okay, so this one is the primary zones and the secondary zones. So here, distribution of stresses in the primary and secondary shear zones we will see. Next to work hardening characteristics of the workpiece material. So because due to this continuous chip formation, uh, that disturbs the operator to machining process also, and some that leads, because of this continuous chip formation, that they have good high heat also. So because of continuity, so automatically those chips injures the operator also. So next one is the geometry of the cutting tool will be disturbed because of this one. Thermal effects, because high heat will be dissipated from this chips also. Next, cutting fluids are needed for this curlings. Okay, so because of this continuous chips, so many drawbacks are there. Just to how to break the chips, and we can continue the machining process very smoothly. So for the breaking of these chips, there are certain process or methods are there. Okay, so chip breakers are very needed because of some drawbacks of continuous chip formation. So okay, this is the chip. So this one like breaker, chip breaker. So this one, this is the tool workpiece. Okay. So we'll see what are the methods and what are the types of chip breakers also. You can see this is the step type chip breaker. So this one is the screw type chip breaker also here. Next to clamp type chip breakers also here you can see. So in the step type, a step is round on the tool face behind the cutting edge. This step will break the chip. So this step will break the chip. This one. In the groove type, with the groove on the tool face, this is the that breaks the chip. You can understand this one. In the clamp type also a thin chip breaker. So this is the chip breaker is clamped on the or screwed on the face of the tool that automatically breaks the chip also. Okay. So here you can see groove type, this one step type, and land type also, the clamp type also. So many types of chip breakers are here. You can understand this one. The chip breaker breaks the produced chips into small pieces. Okay. The work hardening of the chip makes the work of the chip breakers easy. This one. When the strict chip control is desired, some short of chip breakers has to be employed. This one. The following types of chip breakers is groove type, step type, secondary rake type, and clamper type. You can see. So all the chip breakers. Okay. So this one, finding of the chip thickness ratio. R is the chip thickness ratio. Uncut chip thickness by uncut chip thickness by chip thickness, cutted chip thickness. Okay. So this is the formula. This one, the material. So the mass of the material is same. The mass of the material removed is equal to mass of the chip. Both are same. So the formula for this mass of the material is equal to thickness into B is the width into length into density is equal to. So after cutting, so TC and BC and LC and rho C also. Okay. So this one, before, so you can equal this one automatically. Both are density doesn't change. You can cancel this one. Width also doesn't change, and the length also doesn't change. Then so thickness, that is the T by TC. So that shows the R ratio of the thickness is equal to R is equal to uncut chip thickness by TC by T. You can take. So if you consider this one, so otherwise this is the, you can this formula. It is the chip thickness. This is the uncut chip thickness. So you can represent the T is uncut or T is the cut also. You can so represent any terms. So similarly for continuous equation, if you consider the continuity equation, the A1 V1 is equal to E2 V2. This one, area of the chip before cutting, and the velocity, cutting velocity of the chip also, and A2 area of the chip after cutting and velocity. So then V into TV is equal to VC into TC. Then by using this formula, you can understand the relationship between the velocities, cutting velocity before cutting and after cutting also. Finally, the relationship R is equal to, so T by TC, uncut chip thickness by chip thickness into VC by and V. So cutting velocity by uncut velocity, chip velocity. So these are the formulas. We can use these formulas for the solving of numericals also. Here we'll see the how to find the shear angle. So finding shear angle. So phi. Okay. So we'll derive this one. This is the geometry of chip formation, general diagram. You know this one. This is the tool. This is the chip. You know this one. This one is the workpiece. Okay. So this surface shows the AB shows the shear uh, surface, and so you can see shear line also. Okay. Mm. You know this is the reference line. You can dotted line. Then the angle between the reference line, vertical line, and the rack face is equal to alpha. The alpha shows the rack angle, rake angle, rake angle. So here, uh, this one is the cutting force or cutting velocity. Also here we can see in line AB, we'll see the shear velocity Vs. Okay. So that is the shear velocity. So this one is the shear angle, and if you extend the line from B to C, so B to the horizontal line, it will meet the C. So BC is the vertical line. So this is the 90 degrees. So AB is the hypotenuse, and BC is the vertical line. This is the pi. Okay. So by using this triangle, so sin pi is equal to BC opposite side by hypotenuse, then hypotenuse AB, then hypotenuse AB is equal to, so BC into sin pi you can take. So BC is the nothing but uncut chip thickness. So you can see this is the uncut chip thickness TU. Okay. So then AB is equal to TU by sin pi, that is the equation 1 you can take. Then extend line from dotted line from B to the reference line, so vertical line that meets that point, that is the D. Okay. So this is the triangle like this one. Okay. So this is the, you know this one, this is the A, this is the B hypotenuse, this is the D. Okay. So this is the reference line, this one is the rake angle alpha. Then you can see this is the, this one is the pi also. Okay. So then you can here you can see, so this one is the pi. So because A B, this is the represented the D, this representing the C. Okay. So this angle is equal to alpha. Then this is the angle, because this is 90 degrees. You know this one. This angle is equal to 90 minus pi. Okay. So this angle is equal to because this is the reference. Okay. This angle is equal to 90 minus pi. Okay. So here this is the 90 minus pi. Then you have to find out this angle, total angle. This angle is equal to 90 minus pi plus alpha. Okay. So this 90 minus pi plus alpha is equal to 90 minus of pi minus alpha. You have to take this angle, complete angle for this triangle. Okay. For this triangle, you have to take this complete angle. So according to this one, here also AB is the hypotenuse. For ABD is the triangle. ABD is the triangle. Then AB is equal to TC. So this is the cutting chip thickness after cutting. So TC you can take. TU is the uncut chip thickness. TC is the chip thickness. Okay. TC by, so sin theta. Sin theta is equal to 90 minus pi minus pi. So 90 minus pi minus pi is the cos pi minus pi. So this is the angle. So this is AB, this is AB. You can equal this one. So TU by TC is equal to sin pi by cos pi minus alpha. This is the value. Okay, sin. You can see this one. Otherwise, TC by TU is equal to TC by TU is equal to so cos pi by pi minus pi. So this is Tc by Tu is equal to cos pi minus alpha by sin pi. Okay. So sin pi. So this is the formula. So Tc is the uncut chip thickness. Tc Tu. This is the chip thickness, uncut chip thickness by this one. Uncut chip thickness by chip thickness. Chip thickness by uncut chip thickness. So this is R is equal to, you know, that uncut chip thickness by chip thickness. So 1 by R is equal to chip thickness by uncut chip thickness. So from this one you can write 1 by RC. So 1 by RC is equal to cos pi minus alpha by sin pi. So you know that cos A minus B, cos A, cos B plus sin A, sin B. So cos pi sin alpha, sin pi sin alpha. You know this one. So cos pi by sin alpha means cos pi you can write, and sin pi cancel plus sin pi. Okay. So if you cross multiply this one, then 1 is equal to RC cos pi and cos alpha and RC sin alpha. You know this one. Then RC cos alpha is equal to 1 minus RC sin alpha into tan pi. You know this one. So then you can write the tan pi is equal to, this is the formula, tan pi is equal to RC cos alpha by 1 minus RC sin alpha. So this is the formula for finding the shear angle. So then alpha is nothing but alpha is equal to phi is equal to tan inverse of just like RC cos alpha by 1 minus RC sin alpha. So this is the formula. So by using this formula you can find out the shear angle, and by using that shear angle you can find out the chip thickness ratios also. By we can find out the velocities of shear angle and cutting velocities relationship also. So this is the just like details regarding this class. Okay. So main what is the chip formation, advantage of the chip formations, and what is the effect of the build up edges also we already discussed, and we already discussed the how to find out the shear angle also. Okay. So thank you for listening this class. In next class we'll see next forces, regarding the forces in machining. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.